Welcome to our lecture for today. So the idea today is to continue and potentially finish our discussions on solid state chemistry, which marks the second part of our course, which deals with solid state chemistry. So we will finish this before starting our discussion of coordination compounds. All right, so we have studied so far the description of the structure of the solids. We discussed the structure of metals and alloys. We also talked about several structures in ionic compounds, but we will also mention a little bit some of the covalent framework solids today. We will discuss also in our lecture today aspects regarding the energetics of ionic bonding. Then we will talk about defects and non-stoichiometry, and then we will finish by discussing the electronic structure of the solids. So as we have been discussing, there are four main classes of solid materials that comprises solid state chemistry. So we can have the metallic solids, ionic solids, covalent network solids, and the molecular solids. And here the difference between them is the bonds or the interaction between the lattice points or the building blocks that makes up these materials. Metals in the case of metallic solids, cations and anions bound by electrostatic forces in the case of ionic solids, atoms bound together by covalent bonds in covalent network solids, and molecular solids, molecules that are held together by intermolecular forces. So in our last lecture, we discussed a lot about alloys and interstitials. So we discussed several of these concepts, solid solutions, the types of alloys. We also then moved to the structure of ionic solids. So we discussed and gave examples on several types of structures, and all the structures shown here in the table were described by us in the last lecture. And then we saw that these structures can be regarded as being formed by a closed packed arrangement of anions in which cations can occupy holes or interstitials in the structure. So for example, for the rock salt structure, so the structure for NaCl, we have a closed packed array of anions in which we have the cations occupying all the octahedral holes, for example. Okay, so now that we saw a description of all these structures, we can start discussing like the rationalization of these structures. Okay, so in the case of the stabilities of these ionic solids, so we can calculate or predict the thermodynamic stability of these solids or these ionic solids simply by using an ionic model in which ions are treated as being charged hard spheres. And if we have some departures of properties relative to this pure ionic model, it means that we have some degree of covalency in the bonding as well. So it's not purely ionic. So even though this can happen several times, the ionic model is still very nice and very powerful because it's a simple and effective system to predict and correlate many of the properties of ionic solids. So a first important concept that needs to be remembered is the concept of ionic radii, which we discussed in the first lecture of this course, that we saw that generally the trends in ionic radii is that it increased down a group, decrease across a period, and increase with coordination number, and decrease with increasing charge number. But as we saw, the definition of the ionic radii is defined as being measured in a solid material. There is a complication that the size of the ions change with the coordination number, as we also can see in this image, that as we increase the coordination number, the apparent size of the ions increase, right? Because in a solid, if we are measuring the ionic radii by measuring the distance between a cation and an ion in a solid, if we have a larger coordination number, we will have a larger number of positively charged ions around a central ion, which means that the repulsions between these charged ions around the central ion, you push them like farther away from the central ion, therefore increasing the apparent radius that we are measuring, and then that will give rise to the values of ionic radii. Therefore, when we compare ionic radii, we should always compare like with like. So same coordination numbers, for example. All right, so in terms of general trends for ionic radii, it increases down a group. The radii of ions of the same charge decreases across a period. For cations with different charge numbers than for a given coordination number, the ionic radius decreases with increasing charge number. And when an ion can occur with different coordination numbers, the observed radius increases as the coordination number increases. All right. So an important aspect that's why we were talking about the ionic radius again, and remembering the concepts in trends, it's because like a concept called the radius ratio can play a very important role for us to rationalize and predict the occurrence of some of the structures in ionic solids. For example, the concept of radius ratio indicates the likely coordination numbers of the ions in a binary compound or in a binary ionic solid, or solids having only two components, such NaCl, for example. And this parameter, the radius ratio, is widely used in the literature of inorganic chemistry. So this radius ratio is specified by this letter gamma, and correspond simply to the ratio of the radius of the smaller ion, right? Usually the cation, to that of the larger ion. So it's just the ratio between the ratio of radius of the smaller anion relative to the large ion. Smaller ion to the larger ion. So it's just the ratio between this radii. So in this case, what's important is that the minimum radius ratio that can support a given coordination number can be calculated by considering the geometrical problem of packing together spheres of different sizes. So for example, if we would have a radius ratio of 1, this means that for coordination numbers for stoichiometries 1 to 1 and 1 to 2, we would have a coordination number of 12 for the ions. So in this case, no structure like that is known for AB type, and no structure also is known for AB2 structure types. If the radius ratio it is higher than 0.732, then we can have these two types of coordination numbers for 1 to 1 and 1 to 2 stoichiometries, and these are some examples of structures in which this happens. And similarly, we can also do these calculations for other radius ratios. So for example, if the radius ratio is between 0.225 and 0.414, then we can have a 4 to 4 stoichiometry that can give the spherulite or wurtzite structure for zinc sulfide, for example. So, so we calculate this based on the geometrical problem of packing together spheres of different sizes. So for example, in this case, in which the cation is too small like this is an unstable structure, because then the anions here have to touch together before they can touch or bound to the cation. So here we will have the electrostatic repulsions between the anions themselves. So this configures the stability limit, and this is a stable configuration, for example, when we are packing together spheres of different sizes and opposite charges. So we can say that in this case, if the radius ratio falls below the minimum given in these regimes, for example, then the ions of opposite charge will not be in contact, and the ions of like charge will touch, which is this kind of scenario, for example. So using a simple electrostatic argument, a lower coordination number in which the contact of oppositively charged ions is restored becomes more favorable. All right, so these are some examples on how this radius ratio for some type of structure can be calculated. So in the case of cesium chloride, for example, we can have that this is the unit cell, right, in which the cation here is present at the center of a primitive unit cell containing the anions here at the corners. So if we consider here a geometrical, the problem of packing together this system, so we can see that there is a plane containing the cesium and chloride ions here along the unit cell, right? And then if we draw this more clearly, we have this kind of system here, and then we can use this like we can use here this, we can draw this triangle in which we can have that one of the sizes is 2 times the radius of the anion, for example, and then the diagonal here is 2 times the radius of the anions and 2 times the radius of the cation. And then if we do this calculation, we can get that the radius ratio then corresponds to 0.732. 2 in this case. And the same thing, for example, for the sodium chloride unit cell. So here in this case, we can have like this face, for example, redrawn here, and then we can use the same analogy here, drawing a triangle and calculating here what would be the radius ratio or the minimum radius ratio for this kind of structure to be observed, or for this coordination number. All right, so we can use our previous calculations also that we saw on the last lecture on the whole size, for example, to put these ideas into a firmer ground. So for example, a cation, because here we are talking about radius ratio, right? So the ratio of the cation times the ratio of the anion. So this is the radius ratio. So for example, if we have a cation of a radius 0.225 R or below, this will fit into a tetrahedral hole. Note that here this value represents the size of the largest cation that will fit in a tetrahedral hole. And if the ratio is higher, then this will lead to the cation pushing the anions slightly apart. So once the radius of a cation reaches 0.414 R, then the anions are forced so far apart that the octahedral coordination becomes possible and more favorable. Okay? So in this case, if we have this radius ratio, the cation will fit into a tetrahedral hole. If it's lower than this, the cation will rattle into the tetrahedral hole. So actually, this will not be stable. And if the ratio is increased a little bit from 0.225 to 0.414, then the anions will not be touched together. They will be slightly apart. So like shown in this image. And then if it's increased even more, then these they are moved apart even more, which means that the tetrahedral hole is not, the tetrahedral geometry around the anion is not favored anymore, and then the octahedral geometry becomes more favorable. So this octahedral geometry will continue to be the most favorable arrangement until it becomes possible to fit 8 anions around the cation when the radius ratio reaches 0.732 R. So in summary, the coordination number will not increase to 6 or to be an octahedral geometry until the ratio goes above 0.414 R. And 6 coordination will be the arrangement for radius ratios about these values. So these kind of concepts and arguments of packing of spheres based on radius ratios can often be a very good approximation to predict which structure will be more likely for any particular choice of cation and anion, for example. And then here is an example, again, of that table that we discussed before, in which we have these different radius ratio ranges and the different types of coordination numbers that can be achieved, and examples of the structures and compositions that are possible for these kinds of structures. So now we will talk about the energetics of ionic bonding. So we will talk a little bit regarding thermodynamic aspects of ionic solids. So a compound tends to adopt, in general, a structure or a crystal structure, which leads to the lowest Gibbs energy. So the formation of a solid material can be defined thermodynamically by this equation, which involves the formation of the solid material from the elements or the ions in their gaseous forms. So this process, so the process of solid formation through this process is very exothermic, and at or near room temperature, the contribution from entropy to the change in Gibbs energy can be neglected. Therefore, these thermodynamic properties of ionic solids can focus only on the changes in enthalpy following the solid formation. So we can discuss about the lattice enthalpy and the Born-Haber cycle, which enables us to calculate this the enthalpy for the formation of a solid material, of an ionic solid material, for example. So the lattice enthalpy, represented by this expression here, represents the standard molar enthalpy change accompanying the formation of a gas of ions from the solid. Okay, so this is the formation of the opposite of the equation that we saw here previously for the formation of the solid. So the lattice enthalpy is the standard molar enthalpy change that follows the formation of a gas of ions from the solid. So in this case, we have lattice disruption, which means that the process is always endothermic, and therefore lattice enthalpies are always positive. Okay, so, and then usually we don't write the positive sign, we just write the value because it's positive. So if we neglect these entropy considerations, the most stable crystal structure is the one with the greatest lattice enthalpy, because then it will be more difficult to break the solid into a gas of ions. And these lattice enthalpies can be determined from empirical or experimental enthalpy data using this Born-Haber cycle, which can be defined as a closed path of steps that includes lattice formation in one stage. So here we can have the lattice enthalpy represented here as minus X, for example. So we can have like a closed loop of several processes here in which the lattice enthalpy is one of the stages represented as X here, and now the other processes can be measured, and then the experimental values can be known. So from this cycle, the only one unknown is this lattice enthalpy. Therefore, we can, from this approach and using this cycle, we can get the experimental values of lattice enthalpies. So for example, the standard enthalpy of decomposition of a compound into the elements in their reference states is the negative of the standard enthalpy of formation, which is this process here, For example, for a solid element, the standard enthalpy of atomization is the standard enthalpy of sublimation. So here we have the sublimation of potassium, right? Which is this process here. From the gaseous element, the standard enthalpy of atomization is the standard enthalpy of dissociation, which in the case of chloride or chlorine or Cl2 here, it is this process here in which we have the dissociation taking place. Like also the standard enthalpy of formation of ions from their neutral atoms is the enthalpy of ionization for cations and the electron gain enthalpy for anions. So for potassium, the ionization is this process here. And for chlorine, the electron gain enthalpy is this process here. So the only unknown or only value that is not known from this cycle is the lattice enthalpy, which then can be found from the requirement that the sum of the enthalpy changes around a complete cycle should be zero. So with this, we can get experimental values for this lattice enthalpy, and we can calculate now. So this would be like the experimental value, and then we can also go ahead and do a theoretical calculation on what would be this lattice enthalpy, considering purely an ionic model of bonding for an ionic solid. So in this case, to calculate the lattice enthalpy of an ionic solid, we need to take into consideration several different contributions, such as Coulombic attractions and repulsions between the ions, and the repulsive interactions that occur when the electron densities of the ions overlap. These calculations or these considerations gives rise to this Born-Meyer equation that is described here, for example, that we don't need to go into many details, but here D is the distance between centers of neighboring cations and anions. This is the Avogadro number. These are the charges. And this is the fundamental charge, the vacuum permittivity, and this value here is a constant, and typically 34.5 picometers, and A is the Madelung constant that depends on the structure and the distribution of the atoms, and this Madelung constant changes for different kinds of structure, but the heart of the equation is this, right? Which means that how the lattice enthalpy varies with respect to the charge and sizes of the ions in the solid. So with this, we can have a lattice enthalpy that it's calculated and a lattice enthalpy that it's experimental based on the Born-Haber cycle. And a solid is therefore classified as an ionic if we have a good agreement between the purely theoretical calculation based on electrostatic or a purely ionic bond and this experimental value got from the Born-Haber cycle. So if the experimental value matches well with a purely theoretical electrostatic based model, then then it can be stated that the solid is ionic. So alkali metal halides have good agreement with the ionic model, the best being the least polarizable and the worst being the more polarizable halide ions. And this makes sense because then when we have more polarizable ions, then we start to have some covalency character or contribution of covalent bond to the bonding, and then therefore less agreement with this purely ionic model would be observed. All right, so another type of solid materials that we need to discuss are the molecular solids, which consist of atoms or neutral molecules that are held together by dipole-dipole forces, dispersion forces, or hydrogen bonds. So because these intermolecular forces are weak, these molecular solids are usually soft and have low melting points, and examples include argon, water, and CO2, for example. And also we have the covalent network solids, which consist of atoms held together in large networks by covalent bonds. And in this case, covalent bonds are much stronger than the intermolecular forces in these molecular solids, for example. So these covalent network solids are much higher and have higher melting points than molecular solids. So examples of familiar covalent network solids are diamond and graphite, and other examples are silicon, germanium, quartz, silicon carbide, boron nitride, among others. So in the diamond, for example, each carbon atom is tetrahedrally bound to other four carbon atoms, so they have sp3 hybridization being held together by strong carbon-carbon single covalent bonds, and the strength and directional character of these bonds makes diamond the hardest known material, and the stiff interconnected bond network also explain why diamond is one of the best known conductors. So in the case of the graphite, for example, the carbon atoms form covalently bonded layers that are held together by intermolecular networks. So inside each layer, we have carbon bound to 3 other carbons, right? And then among the layers, we have intermolecular forces. And then each layer in the graphite here has the same structure of a single of graphene. So graphene comprises a single layer of carbon atoms held together by covalent bonds here in this plane trigonal arrangement and then we can have in this case sp2 hybridization. So graphite has several of these individual layers that comprise graphene, and then they are held together by these intermolecular forces, which are weak. So that's why this can be easily exfoliated, and that's why pencil, we can write with pencil, because as we apply mechanical force to write, this mechanical force, it's enough to make these intermolecular forces between the layers to break, so we can exfoliate the layers. And this is why writing with the pencil works. So the graphite has the hexagonal unit cell containing 2 layers that are offset, so that the carbon atoms in a given layer sit over the middle of the hexagons on the layer below. And then each atom in each layer is covalently bounded to 3 other carbons in the same layer, forming like these interconnected hexagonal rings. So these are 2 important examples of covalent network solids, and of course we have several others. Another important concept in solids materials is the occurrence of defects and non-stoichiometry. Defects, vacant sites, and misplaced atoms are a feature of all solid materials, and actually their formation is thermodynamically favorable. So all solids contain some defects or imperfection of structure or composition. And defects actually are very important as they influence some properties such as mechanical strength, electrical conductivity, and chemical reactivity. So intrinsic defects means defects that occur in the pure substance, and extrinsic defects, they are originated from the presence of impurities in the solid material that we have. We can have point defects that occur at single sites and extended defects that occur like in 1, 2, or 3 dimensions, for example. So defects are favorable in solid materials because the inclusion of defects leads to an increase in entropy that leads to a decrease in the Gibbs free energy of the system. So therefore, the formation of defects is favorable. However, it is normally endothermic as the lattice is disrupted and the enthalpy of the solid increases. But the term minus TS, so the increase of entropy compensates that. And as entropy rises when the defect is formed. So starting with the discussion of intrinsic point defects, which are defects that occur at a single site for the pure substance, in other words, without the addition of other components to the system. So these, the solid state physicists Stocky and Frankel identified two types of, or discovered these two types of point defects. The Stocky defect, which refers to a vacancy on a crystal structure. So we can have like atoms missing from the structure, so vacancies. So it is defined as a point defect in which an atom or ion is missing from its normal site in the structure. The overall stoichiometry is not affected because in order to ensure the charge balance, these defects occur in pairs or with balanced charges. A Frankel defect, on the other hand, is a point defect in which an atom or ion has been displaced into an interstitial site. So instead of occupying the specific site in the crystal structure, the atom or ion occupies, it's displaced to an interstitial site or hole. And then normally the stoichiometry of the compound is also unchanged when this kind of defect is observed. And this can be observed either involving one or both of the ion types in the binary compound, for example. So regarding point defects, these Stocky and Frankel defects are only two of many possible types of defects. Another example is an atom interchange or anti-site defect, in which the pair of atoms here that makes up the crystal structure, they change places. And this is common for metal alloys, for example, in which there is an exchange of neutral atoms. So this is another type of defect. And also, so this is for the intrinsic ones that occur in the pure substance. But we can also have extrinsic point defects, which result from the presence of impurities. So they are generated when we add what we call impurities into a solid material. And this occurs because the impurity can occur naturally, or we can add another material during the synthesis of the solid. So for example, the incorporation of low levels of chromium into the aluminum oxide structure produces the gemstone ruby. Replacement of some aluminum by iron and titanium results in sapphire. So when we have these impurities that replace some of the original atoms in the structure, for example, normally these impurities, when they are substituting the atom in the original crystal structure, they normally have similar atomic or ionic radius relative to the species which you'll be replacing, such as chromium 3+ in ruby has a similar ionic radius to aluminum 3+. And also we can, this can occur naturally, or we can introduce these impurities by a process called doping to generate some interesting properties. So a dopant or an impurity, which represents the impurity here, represents a small level, typically 0.1 to 5% of an element that replaces another in a solid state structure. So, and then in this case, when we have a dopant species being introduced to the host, the structure of the host remains essentially unchanged. And then if we add actually high levels of dopants, then we usually form other structures, and then we don't have the incorporation of the dopant. And this limits the level of these extrinsic point defects to low levels in terms of concentration. And then usually these dopants often modify the electronic structure of the solid. An example of this point defect is a color center, or a generic term for defects that are responsible for the modification of the optical properties. For example, such as the addition of chromium 3+ to aluminum, to aluminum oxide. For example, an addition of an alkali metal cation at a normal cation site and the associated electron from the metal, they can form or occupy an allied ion vacancy in alkali metal alloys, generating an F-center defect, for example. All right, so these are these examples of extrinsic point defects, but both the intrinsic and extrinsic point defects discussed so far were point defects, so occurs at a single site. But we can also have defects that occur along one dimension in the crystal, such as dislocations, which represent linear defects. So dislocation is a linear or one dimension defect around which some of the atoms are disaligned. So here we have an example where a dislocation is observed. So it's a linear defect that centers on the line that is defined along the extra half plane of atoms. So this is the definition. So here we have a defect in the crystal in which you have an extra plane of atoms, for example, and then here we have a dislocation in which around here atoms become disaligned relative to the normal solid structure, for example. So here we have this misalignment being more clearly defined, and here is the site where we have this edge dislocation. We can also have interfacial defects, which occur at the boundaries or interfaces of a solid, and these have two dimensions. So this corresponds to separate regions of the materials that have different crystal structures and crystallographic orientations. So these interfacial defects include external surfaces, grain boundaries, phase boundaries, twin boundaries, and stacking faults. So in the case, for example, of external surfaces, we have to remember that at the surface of a solid material, the atoms are not bound to the maximum number of nearest neighbors. So the atoms, because they are on the surface, they have a lot of missing bonds, or they are not, their coordination number is smaller than it is for the atoms in the interior of the solid, which leads to a higher energy state for the atoms at the surface relative to the atoms in the interior of the solid. And this gives rise to increased reactivity, and this is usually pursued in catalysis very much. So this leads to increase in catalytic activity, because this can lead to increased reactivity towards a variety of molecules. So for example, here we have a nanoparticle of this cerium and zirconium oxide, in which, like on the surface of this nanoparticle, we can have different types of these surface defects, or terrace versus ledge versus crevice versus kink sites, or the presence of atoms and steps. And at these defect sites, for example, we already have a lower coordination number at the surface, but then at these defect sites, we can have even more, like even lower coordination numbers, which means like regions of increased energy and therefore increased reactivity. And this leads to increased capacity to act as catalyst, or this gives rise to a catalyst with good performance towards a variety of molecules, because then catalysis involves the chemisorption and splitting of molecules at the surface of these solid materials. So as metals or several particles containing these metals can absorb different molecules that are important in several catalytic processes, having these surface defects, for example, can increase this process, or increase the activity of these solid materials, leading therefore to increased reactivity. And catalysis is a field that has revolutionized human history, has revolutionized our quality of life. So over 85% of all the products made in industry involve catalysis in one or more steps. And these include, such as shown in this table, synthesis of sulfuric acid, ammonia, and many other molecules that are central to the chemical industry of today. And catalysis is also involved in several strategies to provide a clean environment, to degrade pollutant materials, to enable recycling of plastics, for example, and also to mitigate climate change, in which we can turn CO2 into fuels and other important chemicals, for example, by using catalysis. So the development, study, and discovery of these solid materials and the rational incorporation of these surface defect or defect sites that lead to increased reactivity is a very important area of research nowadays. So this is a very timely and important important topic. Regarding interfacial defects, we can have like twin boundaries in which a twin boundary is formed, is a specific type of grain boundary across which we can have a plane of symmetry having mirror lattice symmetry in this case. So atoms in one side of the boundary are located in mirror image positions of the atoms on the other side. And then with this, this is what I wanted to mention about these defect sites. And then in the next slides, I would like to discuss with you non-stoichiometry and solid solutions. But before that, I think we should take a 10-minute break. So let's get back at 1:15, all right? So see you guys in 10 minutes. Hello, everybody. So welcome back to our class. So now an important concept and phenomenon that also occurs in solid materials is the occurrence of non-stoichiometric compounds and also solid solutions. So the statement that the stoichiometry of a solid material is fixed by its chemical formula is not always true when we are talking about solids in which differences in the contents of unit cells can occur throughout the structure of this solid, and these changes in composition of the unit cells along the solid material can arise from vacancies at one or more atom sites, the presence of interstitial atoms, and the substitution of one atom from another, for example. And the deviations of this ideal stoichiometry are common for solid materials in the D, F, and heavier P block, for example. So what is a non-stoichiometric compound? A non-stoichiometric compound is a substance that exhibits variable composition but retains the same structure type. For example, at 1,000 degrees C, the composition of iron monoxide, which is sometimes referred as wood varies from 0.89 to 0.96. So it's referred this way. So the fact that the lattice parameter of the compound varies smoothly with composition, this is what defines a non-stoichiometric compound. And this is because when we have a discontinuity in terms of the lattice parameter, then we have the formation of a new crystal phase. So if we have that the lattice parameter varies only smoothly with the composition, that means that the same structure is obtained, and therefore we have this non-stoichiometric solid. So the Vergaard's rule stipulates or defines the change in the lattice parameter as a function of the composition. And here we have a representative composition range for several binary hydrides, oxides, and sulfides that are non-stoichiometry, that shows non-stoichiometry, for example. And this formation of these non-stoichiometric compounds requires overall changes in composition. It also requires at least one element to exist in more than one oxidation state. Therefore, this is more usual for elements in the D and F block, which normally adopt two or more oxidation states, and also in the P block, or heavy P block elements that can have more than one oxidation state as well. And as we discussed last time, as we were talking about alloys, solid solutions occurs in solid materials when there is a continuous variation on the stoichiometry without a change in structural type. This occurs in many ionic and solids, such as metal oxides, for example, and because many substances adopt the same structural type, is often feasible to replace one atom with another. This is also seen in many metal alloys, for example, in which, like, for example, zinc and copper brasses exist for a complete range of compositions where, like, the copper atoms in the structure are gradually replaced by zinc atoms. So in a solid solution, all the sites in the structure remain fully occupied. The overall stoichiometry remains constant, but we have different proportions of atom sites, atom types on some sites. And there is a smooth variation in lattice parameter over the specific compositional range that is described. And these solid solutions is frequently observed for D metal compounds, and the change in one component might require a change in the oxidation state of another component to preserve their charge balance. And now, one of the last parts of our discussion in solid state material is the discussion of the electronic structure of the solids, because the understanding of the electronic structures and the derived, this enables us to understand a lot of properties such as conductivity, magnetism, and also optical properties. So when we are talking about the electronic structure of solids, we need to consider the interactions between the electrons of the components and the extended arrays of atoms or ions that forms these solids. So an approach to describe the electronic structure of the solid is to use or to regard the solid as a huge single molecule in which we can extend the molecular orbital theory of small molecules to account for the properties of the solids, and then the solid can be regarded as the combination or aggregation of an almost infinite number of atoms generating this huge, very large molecule, for example. This is strikingly successful for the description of electronic structure of metals, enables us to explain their characteristic lustre, their good electrical and thermal conductivity, their malleability. All these properties arise from the ability of the atoms to contribute with electrons to form a common sea or region in which electrons are delocalized over the entire extension of the molecule. And the lustre and electrical conductivity in metals occur as a result of the mobility of these electrons in response either to an oscillating electric field of an incoming electromagnetic light or to a difference in applied potential. So the high thermal conductivity is also a consequence of this electron mobility, as because an electron can collide with a vibrating atom, pick up its energy and transfer it to another atom elsewhere in the solid. The ease in which metals can be deformed is also because of this electron mobility, as the electron cloud can quickly readjust to the deformation of the solid and then therefore keep the atoms bound together. And the electronic conduction is also a characteristic of metals, but also semiconductors, in which the distinction between a metallic conductor and the semiconductor is the temperature dependence of this conductivity. So, for example, a conductor is a substance in which the conductivity decreases with an increase in temperature, and the semiconductor has the conductivity increasing with temperature. But at room temperature, the conductivity of metals are higher. And in the case of a solid insulator, we have very low electrical conductivity, and superconductors refer to a special class of materials that have zero electrical resistance below a critical temperature. So this is how we can explain the formation of current, for example, in metals. So in a solid structure, the metal atoms are stuck into fixed positions, and we have electrons that are free to move along the structure because they form bands of energy. So they are delocalized over the structure. And then when we apply the voltage, the electrons can move from a high to low potential regions, giving rise to the current. All right, so in order to describe these bonds formed in the solids, we can remember that bonds are formed by overlapping of atomic orbitals. So the central idea to describe the electronic structure of the solids is that the valence electrons supplied by the atoms is spread throughout the entire structure, and this is expressed by making a simple extension of molecular orbital theory in which the solid is treated as an indefinitely large molecule, in which, as we have molecular orbitals combining, atomic orbitals combining, we generate molecular orbitals that increase in size. So as more atoms interact, so as we increase the number of atoms interacting, we generate a higher number of molecular orbitals in which their energy starts to get closer and closer together until they actually merge because they are so close, forming a band of continuous energy. So a band is a region of practically continuous energy in which the electrons can move freely along this region. So this, the formation of this band of energy by the overlap of an infinite number of atomic orbitals, as in the solid, we have an infinite number of atoms. So in the overlap of a large number of atomic orbitals lead to a large number of molecular orbitals. They are so closely spaced in energy that they form almost a continuous band of energy levels. And these different bands can be separated by band gaps, which are values of energy in which there is no molecular orbitals, so not occupied by the electrons. So here is another representation of the formation of these bands with filled and empty molecular orbitals, for example. And here is another representation of this band of energy when we have an infinite number of atoms forming our solid material. So the formation of the bands can be understood by considering a line of atoms and supposing that each atom has an s orbital that overlaps to the s orbitals of the neighbors, and then, like, when we have an infinite number of atoms joining together, then we have an infinite number of molecular orbitals that become very closely spaced to each other, forming this almost continuous region of energy levels. So if we are considering s orbitals, we will generate an s band. Of course, if there are p orbitals available, then we will form a p band. And then because p orbitals lie in energy higher than the s orbitals in the same valence shell, if we have an s band and a p band, there is often an energy gap between the s band and the p band. And the d band is similarly constructed from the overlap of the orbitals. An important concept is the concept of Fermi level, which refers to the highest occupied energy level for a solid at temperature equals 0 Kelvin. So it lies near the center of the band. When the band is not completely full, the electrons close to the Fermi level can easily be promoted to nearby energy levels. As a result, they are more mobile and can move freely through the solid, and the substance will be a conductor. Another important concept is the density of the states, or the width of the bands, in which it's important to mention that the number of energy levels in an energy range divided by the width of the range is called the density of the states. And the density of states actually is not uniform across a band of energy, because the energy levels can be more well packed together closely to the center of the band relative to the edges of the band. So here we can see that the energy state increases in the region like closer to the middle of the band. And then the density of states is lower at the edges of the band. So in the case, so here we saw that when we have partially filled bands, the substance can be an electron conductor, as electrons can freely be excited above the Fermi level to these empty states, which is the same band of energy. In the case of an insulator, a solid is an insulator if we have electrons that are present to fill the band completely, and there is a significantly large band gap before the next empty band becomes available for electric conduction. In an insulator, the band of highest energy that contains electrons is normally termed the valence band, and the next band is the conduction band. In the case of semiconductors, we have an intermediate situation. So the characteristic physical property of a semiconductor is that its electroconductivity increases with temperature. So at room temperature, the conductivity is intermediate between those of metals and insulators. And what changes, what differentiates insulators and semiconductors is the size of the band gap between the filled valence band and the next empty band, which is the conduction band. So the values of the band gap and conductivity are indicative of the semiconduction. So here we have the scenarios in which we have the metal with a band which is half filled, so electrons can move to the empty regions of the band very easily. So it's a good conductor. For the insulator, we have a complete filled valence band, and then these electrons cannot be excited to the conduction band because the gap is very large. And for a semiconductor, we have a filled conduction valence band, but here we have only a significantly small band gap, so that with temperature, electrons can be excited to this conduction band, and therefore electrons can access this region of energy, and therefore conduction can occur. So in intrinsic semiconductors, the band gap is small, so that the thermal energy enables some electrons from the valence band to be excited to the conduction band, as described here. This leads holes in the valence band and generates electrons in the conduction bands. And then both the holes and the electrons can move, and therefore the material is able to conduct, or it becomes a conductor. So a semiconductor at room temperature has lower conductivity than a metallic conductor, because only few electrons and holes can act as charge carriers. And then like this dependence with the temperature of the increase in conductivity follows an exponential Boltzmann-like temperature dependence, because then we start to promote more electrons to the conduction band. All right, in addition to these intrinsic semiconductors, we can also have extrinsic semiconductors in which we intentionally add impurities to the materials or dopants, which leads to the semiconducting properties. So the number, in this case, of electron carriers can be increased if atoms with more electrons than the host element are introduced. And remarkably, even low level of dopants are needed or enough to generate this extrinsic semiconductivity. So for example, if we add arsenic atoms into a silicon crystal, so arsen has one extra p electron in the p level than silicon. So this one additional electron will be available for each dopant atom that is introduced and substitutes silicon in the structure as shown here. So what happens is that if the donor atoms are far apart from each other, their electrons therefore will be localized in energy and the donor band will be very narrow. Moreover, this foreign atoms level will be at higher energy than the valence electrons of the whole structure, as shown here. And normally, this dopant band, in this case, will be very near the empty conduction band. Therefore, if the temperature, even at room temperature, some of the electrons will be thermally promoted into the empty conduction band, leading to the property or leading to the semiconductor. And this, in this case, this is called an N-type semiconductor because the conduction here arises from electrons, negative charges that are added by the dopant. So in other words, the thermal excitation will lead to the transfer of an electron from an arsenic atom into the empty orbitals of a neighboring silicon atom. From there, the electron will be able to migrate to the structure in the band formed by the silicon-silicon overlap. This process is therefore N-type semiconductivity, and N indicates negatively charged. And in the opposite scenario, we can also have the addition of dopants having fewer valence electrons, such as gallium here. So in this case, the dopant atom of this kind introduces hole in the solid. So we have the band of the dopant here, which will be an acceptor band. So here electrons from the host material can be excited to this acceptor band, and then the left holes in the valence band will act to give the conduction properties of the solid material. So this acceptor band can accept thermally excited electrons from the valence band. Here is shown the introduction of the boron atom to the silicon lattice having one electron less, introducing a hole to the structure. So this introduces a hole into the valence band, which allows the remaining electrons in the band to be mobiles. And then in this case, the charge carriers are the positive holes in the lower band, and then this type of semiconductivity is called p-type semiconductivity. And semiconductors are very important. They are essential components in all modern electronic circuits and transistors, for example. So here we have a scenario of an undoped semiconductor with the valence and conduction band, N-type semiconductor, and p-type semiconductor as a comparison. And here are some values for band gaps for selected semiconductor materials. For example, these semiconductors are important components of many of many electronic devices, such as diodes, for examples, that refer to p-n junctions, or a junction between p semiconductor and any semiconductor. For example, this allows current to flow in only one direction. And so this is very important in terms of electronics. These junctions are also important for the development, for example, of LED lighting, in which the heart of a LED is a PN diode, which is formed by bringing an N-type semiconductor into contact with a P-type semiconductor. So when we apply a voltage, electrons are driven from the conduction band of the N-doped side into the junction, where they meet the holes that have been driven from the valence band of the P-doped side, and then these electrons then fall into the empty holes, and this energy is released as photons, having the wavelength corresponding to the energy level of the band gap. So this way, electrical energy is converted into optical energy. And this is also one of the principles that that is based on the on how solar cells work, right? In which photons are absorbed here in the junction. So this excites one electron from the valence band to the conduction band, generating a hole here and an electron. And then this electron is therefore, with an applied potential here, migrates to the conduction band of an N-type semiconductor, and the hole migrates to the valence band of a P-type semiconductor. So in this case, we have the conversion of light into electric energy. So first, photon is absorbed in the junction, exciting the electron from the valence band into the conduction band, generating the electron hole pairs. And then the electron is attracted to the N-type semiconductor and the hole towards the P-type semiconductor. And then in this way, we convert the energy of the photon into electric energy. And this excitation across the band gap in semiconductors has been widely employed in photocatalysis as well, in which these electrons can activate surface molecules, and these holes can also activate surface molecules, in this case, forming radicals, hydroxyl and oxygen radicals, for example, that can drive reduction and oxidation processes. And this leads, for example, on the degradation of pollutants from water, for example. And these photocatalysis can also be employed to drive water splitting as well. So these electrons and holes can be involved in oxygen evolution and hydrogen evolution reactions as well. So at the nanoscale, so we have a nanoparticle. So if we have a nanoparticle, like we have less atoms forming the solid material relative to a macroscopic or a larger solid. So in the nanoscale, we have the region in which we have the frontier between the scale of molecules and the scale of more macroscopic solids. So in the case of semiconductors, for example, when we have sizes between 1 and 10 nanometers, instead of having this band of energies, we start to have a little localization of the energy levels. And this leads to properties such as size-dependent emission in these materials. because as we reduce the size of these nanoparticles, for example, as energy levels, it starts to become more localized or more discrete relative to continuous bands of energy, the band gap is sensitive to the particle size, and therefore this leads to the fact that particles of different sizes have different emissions, and these can be applied in different types of applications for imaging, for example. In the case of metals, at the nanoscale, we saw that these electrons can move freely along the structure as a result of the metallic bonding, and then when we have smaller scale, this movement, when we have the interaction of the electron cloud with the light, this movement can lead to absorption and scattering of the electromagnetic radiation, and then this gives rise to interesting colors of gold nanoparticles. So for example, gold has this golden color, while gold nanoparticles can appear red, and this is because the way that the sea of electrons in the nanoparticle, that because of the size, because it's localized, interacts with the electric field component of the light. So this gives rise at certain frequencies to absorption and scattering of the light, giving rise to these interesting colors. And in fact, since ancient times, these interesting colors of gold nanoparticles have been employed to give colors to these glass windows. So the red colors here are made of gold nanoparticles, and this remarkable example of the Lycurgus cup made by the Romans, in which we have an interesting dichroic effect. As we shine light from inside the cup, we see red due to these absorption and scattering properties of gold, and then if we shine light from the outside, we see green. So the green corresponds to scattering, and the red corresponds to absorption of light, actually. And this has in the composition gold and silver nanoparticles, and not only gold, actually. So in this case, what happens for these metal nanoparticles is that when we have the light with its incoming oscillating electric field component interacting with the free electrons in the metal, we have the collective oscillation of the metal when this is in the nanoscale with respect to the light. So this occurs in a particular frequency, and this leads to absorption and scattering of light, as well as the generation of strong electric fields to the environment and on the surface of the material. And this also, like, in addition to absorption and scattering and the generation of these intense electric fields, we also have the dissipation of heat to the environment. So these absorption and scattering properties have been employed, for example, in imaging properties, these intense electric fields to enhance the spectroscopic signal of several molecules, enabling under certain conditions detection at the single molecule level, and the localized heating as a result of these interesting optical properties has been employed, for example, to photothermal therapies to treat cancer, for example, in which we can add these nanoparticles selectively to regions containing the tumor. Then we can shine a light in this system, for example, and then the light will excite these electrons, and this excitation will dissipate heat to the surroundings, and this heat will therefore kill the cancer cells close to the nanoparticles. So with this, we finish our discussion on solid state materials, in which we describe the structure of the solids, metal and alloys, ionic compounds. We talked about molecular solids and covalent framework solids as well, their definitions and a few examples of structures. We talked about the energetics of ionic bonding, how to calculate lattice enthalpies by the Born-Haber cycle, different kinds of structures, the ratio to predict coordination number and structures. We talked about some definition of defects and their importance for properties, the occurrence of non-stoichiometry, and in the end, we discussed the electronic structure of the solids. So this is everything that I had for today. I think the class today was kind of heavy, a lot of concepts and a lot of material that we had to go through. So the speed was maybe a little or quite fast. So if you guys have any questions, you can ask me now before we wrap up, or you can ask me later before the exam, or at any time by email. So does anybody have any questions before we finish for today? Well, if not, thank you very much, everybody. And I see everyone again on Friday, okay? All right. Bye-bye, everyone.